I've become absolutely fascinated by looking at this business of the availability of the elements that we have, the metals we have to play with, to work with. And I think it's perhaps interesting to notice that before we ever learned how much of these materials were on the face of the earth, we learned how to use them. If we looked at the first slide, we'd see that there are only 8 elements out of the approximate 100 elements in the periodic table. There are only 8 elements that occupy approximately 98.6% of the Earth's crust. And all the rest of the 100 make up the 1.4%. If you look at this slide, you find out that the most abundant element in the crust of the Earth is oxygen. Well, that's pretty fortunate for us, I guess, since we require a lot of oxygen to live. And it tells us that we're not going to run out anytime soon, I guess. The second most abundant material element in the face of the Earth is silicon. I guess that's pretty fortunate for us, since we have discovered that silicon is a material that's going to enable us to do such things as take the radiant energy of the sun and convert it directly to electricity, and does such good service in all of our computers, microchips, and the like. So it's the second most abundant material in the face of the Earth. And aluminum comes along as the third most abundant material in the face of the Earth. And since that's one of our structural materials, it's pretty advantageous that we can use that. However, we find that we have other uses for that I'll show you in a moment. And the fourth most abundant material in the crust of the Earth is iron. Having about 5% of the Earth's crust is going to be iron. And certainly that is our basic structural material that we use today. Calcium comes along as the next one with about 3.6% of the Earth's crust. Then sodium and potassium and magnesium. Actually, we use these elements in many different ways, not just as metallic materials. For instance, if we look at, let's say, the most used element in the most used material in the world today, tonnage-wise or volume-wise, makes little difference. It is today what it always has been, and it's wood. That's the most used material today. The second most used material in the world today is concrete, Portland cement type concrete. And what's concrete made it of? That's an aluminum calcium orthosilicate. So we have aluminum, calcium, silicon, and oxygen. Basically, that's what the concrete's going to be made out of. And we look at something like glass. And what's glass made it of? Well, you're all familiar with soda lime glasses. So that's sodium and calcium and silicon is going to be the basic material that's going to be in almost all of our glasses. If you say, well, I would like to look at another material that's an abundant material that we have on the face of the Earth, then we find a modern one is polymeric materials. And we're back now to the material that's organic, carbon. But carbon is one of the rarest elements in the crust of the Earth. Way down, much, much less than anything we have. Actually, many of the metals are this way too. If we look at the distribution of some of the other elements that we find are necessary metals that we use every day, in this slide we find out that, for instance, nickel is a metal that we depend upon very, very much, particularly in making our stainless steels and our corrosion-resistant steels. We find that this, in the same scale, occupies only 0.02% of the Earth's crust. Copper is one that's only 0.01%. Tungsten, one that we can hardly do without in our current technology and our current living methods, we find that's at 0.005%. Zinc at 0.004%. Lead, the material that I just talked about in the last lecture, which we use in such unique ways, is 0.002%, and tin way out to a very much lower percent. And as we go down to silver and the noble metals, we find that we get way out to about 6, 7 up to 10 decimal places. And if you do carbon, it's going to be even lower than that. So whether the utility of the material is for the materials that we have the most of, we find that actually those materials at the top of the scale that we use in the biggest tonnage happen to be in the most, are the most prevalent in the crust of the earth. But these particular materials that we've just looked at are the materials that we need, we have to have, and we have to search them out. We have to find them where they're concentrated in the ore deposits. But as I remarked in between the classes, to ask if we have an abundance of a material, the crust of the earth is so big that if we could gather together, for instance, all the gold of the earth at one spot, we would say, well, gee, we have an abundance of gold. And we have an abundance of almost anything. So it's hard to say that we have a shortage of material unless you consider the temporal aspect of that. That is, the time that you have it. Where you are, do you have as much as you want? It's sort of like money, right? There may not be a shortage of money, but if I don't have any, then to me there's a shortage of money, right? Well, these fascinating materials now that we have, I think you should get to be able to talk to them. I think they ought to talk to you like the tin talk to you. Except they're not going to jump up and down and say, I want to say something to you. It'll be more like the crystals on that post out on the road. That is, it's there, and it tells you something if you want to look. But what's the most prevalent mineral that you'd find on the face of the earth? Well, you'd expect it to be associated with the most prevalent element that you found on the face of the earth, and it is. So we'd expect to find it as silicon dioxide, or quartz, or quartzite. And so you ought to, develop an appreciation and a recognition. Say, you go down the street and you look at a piece of quartz and it's like, hi, Mr. Quartz, you're Mr. It. You're more than anything else on the face of the earth is quartz, or a piece of granite that will contain these particular materials. Or if you look at calcium, which was in the list of the 8 materials that we have, then where's the calcium going to be? It's going to be as calcium carbonate, which will be limestone or marble, or a material that you can reach out and touch every day, and it's one of the real prime materials that's out there. So actually, in all of these things, I think if you can get involved in the spirit of just living with them, they begin to tell you things, and they answer questions for you. But if we go back now to trying to squeeze them all out so we can make good use of them, we run into a field of the classifications of fields of metallurgy. We say that there are 2 types of fields in the field of metallurgy. It is the adaptive metallurgy, and is it the extractive metallurgy. And if we look at the extractive metallurgy system that we have, we find that there are many, many divisions of this. And for instance, we start off looking at, let's say, under extractive metallurgy, the first thing would be mechanical metallurgy. And under mechanical metallurgy, and we sort of gone through this now, the very first thing we're going to do is to participate in some ore dressing. And so when we do the ore dressing, we want to examine all the different things we can do to dress the ore. Then we have the problem of doing sampling. It in itself is no mean chore. You've got to be able to say that whatever I'm representing here is a sample of what I want to do, want to refine. Then we have the chemical metallurgy division under extractive metallurgy, and in this particular area we find that we have a division of pyrometallurgy, which involves drying, calcining, roasting, smelting, converting, distillation, and finally to do the very fine fire refining that's at the very end. But all of these particular processes that we have in here are doing something to the ore, preparing the ore so that we can, in the end, get a unique, pure material, or almost pure material. And we're going to follow one of these things through all the way and look at all of these different steps when we look at the refinement of copper. Also, in the next slide, we see that there's a continuation of this part of metallurgy, this extractive part of metallurgy. And we have After the chemical metallurgy, we have hydrometallurgy. And in this hydrometallurgy, we do things like amalgamation, leaching, evaporation, crystallization, and precipitation. Now, I already described some of these things to you, but we will look at those again just briefly as we go through the preparation or looking at some of the materials, like, say, the refinement of aluminum. And we find that there's an electrometallurgy section in this business of extractive metallurgy, and we have an electrolytic process where we actually extract the material from aqueous solutions. That is to say, we dissolve a material in solution and we plate it out. Or we have the situation where we have anodes, but the anodes are soluble and they go into solution in the electrolyte that we are going to use, and when they come out of the electrolyte, they come out on one of the terminals of the cell, and so we are continually dissolving the anode. And then we have an insoluble anode, and that means we are taking the solution itself and we're extracting the material from it. We have electrolysis from fused salts. We do an extraction and refining of those, and we'll talk about those just slightly. And we do an electrothermic process, which is refining and smelting of the material. That involves both electrical and thermal aspect, and we do it both at the same time. And in the refinement of aluminum, we'll find that that's something that we have to really take a close look at. Well, let's go on an adventure to get copper. Now, I'd like to tell you about a place that you really should see if you ever have a chance, not too far from here. You should go to Salt Lake City and go to the Bingham Canyon Mine. This is an open pit mine. In 1890, it was a mountain that was almost a mile high, and now it's a hole that's almost a mile deep. But the exciting thing about this is that in this particular metal, man has learned to take that material, which had such a low concentration on the face of the earth, to take an ore now that is going to be the ore, something he can get the copper out of economically, make money on it, where the ore content, the copper content in the ore, is less than 1%. So 99% of everything that he digs out of the ground is going to be a gangue material, something that's going to wind up as tailings, something that he's going to throw away. And if you can imagine a process like that, then you say, gee whiz, if we can do that with copper, why can't we learn to do that with aluminum? And then my backyard that has that $500,000 6 feet under in a 1 acre land, I could mine it and get the aluminum out of it. Or we could look on the total face of the earth at all of the elements and we'd say, hey, these things are now abundant. So we have a long, long way to go. We've got to move ahead in all of these fields, like this particular field, which involves a lot of chemistry, pyrochemistry, electrochemistry, all sorts of things, to learn how to do these processes so we can come up with the ability to refine low-grade ores.